Hello, everybody. Welcome to week 9 of the economics of cryptocurrency. Today we're going to deviate a little bit, or this week, I should say, we're going to deviate a little bit from the book and Bitcoin, which we've been heavily focused on up to this point, especially during the last few weeks. I wanted to say I hope you had a nice spring break too. I just jumped right into it there, but I hope you had a nice spring break. So one thing I just wanted to motivate a little bit of the lesson today is this article came out just a few days ago, 2 days ago, it looks like. Kraken, oops, nope, I'm not sharing my screen, so you can't see anything. Here we go. Kraken right here becomes the first crypto firm to win access to Fed's core payment system. And I just wanted to point this out because the institutional environment in which cryptocurrencies operate and really for the overall financial system is changing because of the things we've learned about. And we're going to really get more heavily into that by describing a different type of distributed ledger today called R3 Corda. R3 is a company, Corda is a software that they created. Now, this is, as we'll see, this has some similarities to Bitcoin, but a lot of differences. And there's institutional reasons for that. But this is a big part of growing cryptocurrency sort of economics and finance, but not one that's headline grabbing, like when Bitcoin prices go up a lot or go down a lot or things like that happen. So this is really where a lot of what we've been learning about sort of meets traditional financial institutions. And traditional financial institutions are those that might be interested in using this software called Corda that we're going to discuss today. And we're really going to be discussing the institutional and economic aspects of it. And we're more prepared to do that now because of the tools that you have learned so far in the class. So let's just get right into it. So one thing, R3 Corda, it's a distributed ledger like Bitcoin. Bitcoin is a ledger of transactions, a history of all the movement of the Bitcoins, when they're created, where they've moved around. And it's distributed publicly to everybody and it's permissionless. Anybody can join that network. You or I could today, maybe you already have joined the Bitcoin network. Corda is very different than that because it's really designed for regulated financial markets. So far in this course, we have studied cryptocurrency systems primarily through the lens of Bitcoin-style systems, namely Bitcoin and Ethereum, one that you read about more recently and we discussed when we talked about smart contracts, for example. Ethereum and Bitcoin have several defining characteristics, and hopefully this won't be news to you, but they're permissionless participation, so anyone can join the network. Identities are hidden, so we use these addresses which are not hidden, but by using an address, identities are hidden. So instead of legal names, like when you go to a bank, you have to prove your identity when you start an account. When you go to Bitcoin, like you don't have to say anything about your identity, you just need to create an address. Global broadcasts of transactions and blocks. So everybody, as we've looked at many times, everybody can look at the different transaction of blocks that have been created as we have done. That is not going to be true at Corda. Those transactions will be hidden on Corda, and very few, only those that are allowed to look at them will be able to see them on this Corda system. We've seen how agreement is reached, agreement about the history of the coins. And remember, that's where the digital coin is a history of transactions. And we talked about that in the past. That's important to keep front of mind because that's a kind of a tricky concept to think about. But agreement about that history, which defines the value on the network. So clearly that's very important. We've seen how mining, proof of work, and the longest chain rule work together to create that sort of agreement. Transparency also, everyone can both see and verify transactions, the history, and all of that publicly, basically, because it's all open access essentially. So in week since, we actually built a toy version of that so we could play around with it. Miners competed in proof of work race, blocks propagate across the network with delays, because delays were important. Forks occur when blocks are discovered at similar times. And we saw this. We actually were able to create forks in the blockchain in our little toy model. As a result of those forks, some valid blocks become orphaned. The transactions have to go back into the mempool where unverified transactions float until they were put on a block. Ultimately, they will be on a block on the blockchain as long as they are authentic and verified. So the key insight was that Bitcoin achieves agreement not by preventing disagreement, but by resolving it over time using public rules and economic incentives. So that's like the really big picture there. So last week or the week before midterm and before you took the test, we shifted our attention to the financial economics inside blockchain systems. Really, that's occurring in Ethereum because Ethereum is the blockchain that allows for things like smart contracts. So that also will help us shift over into Corda because essentially what is happening on Corda are smart contracts. So one important takeaway that will matter again today is that smart contracts enforce rules mechanically. We don't go to a judge or something and have them subjectively potentially enforce rules based on other things outside the transaction. No, smart contracts are a list of code and it will occur if certain prerequisites are met, the transaction is verified or the smart contract is executed. So based on logic and inputs like prices and balances, but not based on judgment. A different institutional design exists for financial markets, and a lot of this is based on, so this is newer, and this is now the application, a lot of these tools that have been discovered and created as applied more to traditional finance. So R3 Corda represents a different branch of a distributed ledger design. So Bitcoin is a distributed ledger that's a blockchain. Corda is not actually a blockchain because as we'll see, we don't collect transactions on blocks and then show them publicly and then do things like hash the old block to make sure that the history is verified, things like that. So Corda is not a blockchain, but it is a distributed ledger with digital transactions and digital currencies, basically. Digital currencies defined as we did very early in this class, where it's like changes in spreadsheets, basically, or changes in a ledger. So instead of focusing on anonymous open networks, Corda was built for regulated financial institutions where participants are legally identifiable organizations. So you have to prove your identity to participate in Corda. They often require privacy between counterparties because maybe Bank A and Bank B want to make a transaction with each other, but they don't want that transaction. They don't want everybody to see that transaction because maybe it has to do with their business strategy, their trading strategy at their bank, and they don't want that to just be open knowledge for everybody when they make those transactions, because having that being open knowledge might disrupt their business strategy, interfere with maybe they're making a bet. They don't want everybody to follow them into that bet because it might be more affordable. Maybe they can more buy low. For example, JP Morgan maybe wants to make a big bet on something, but they don't want everybody to know they're going to make a big bet on that thing before they do it, because then they might have to pay a higher price to place that bet. There's all types of different reasons privacy would be important in regulated financial institutions. These also must operate within regulatory and legal frameworks because we're talking about highly regulated institutions now that Corda, R3, the company, created Corda software specifically for those types of institutions. So they were thinking heavily about, well, what can we do for these regulated financial institutions that exist and really control the entire financial sector, or make up, I should say, the financial sector, who may be less interested in interacting with permissioned or permissionless blockchains like Ethereum. And maybe they're even blocked from doing things like that for regulatory reasons. So they must operate in a regulatory and legal frameworks. And we also want deterministic finality rather than probabilistic confirmation. So as we've seen, we make a transaction in Bitcoin. it goes into the mempool. Eventually, a miner will put it on a block and try to mine the block, but that's all probabilistic. That's not happening. And we've even talked about when is a transaction truly verified on the Bitcoin network? And there's sort of different by the once there's 10 blocks past the block where the transaction is verified, it's extremely unlikely that that transaction will be unwound. It could be because maybe that's an orphan block because maybe we have two really long forks. That's extremely unlikely, but it's still possible. So that's why it's probabilistic confirmation of transactions rather than deterministic finality like would occur in the banking system. But maybe not quite. Maybe because there are things in the banking system like counterparty risk. Maybe I make a transaction with somebody else, they agree to pay me, but maybe they never actually pay me. And those sort of things at the institutional level are what sometimes lead to things like financial crises. Like if everybody gets worried that Bear Stearns or Lehman's not going to be able to pay them back, that might cause the entire financial system to freak out. So those are the big picture sort of stories we might want to think about when we're thinking about what is the usefulness of a Corda type system. So in a Corda system, we have permissioned participation. You need to get permission to engage in this blockchain. You probably have to be a well-established financial institution, like a bank, a pension fund, an insurance company, hedge funds, things like that. You have to prove your identity is part of getting that permission. So known institutional identities, selective information sharing instead of global broadcast to maintain privacy of transactions. So my identity is no longer private, but the transactions that I make as an identity become private and are only known to parties that need to know or are part of the transaction usually. So we get agreement. So similar to blockchains, we do rely on digital signatures, and those are used for verification. But instead of using this decentralized validation through blocking transactions, verification that's public, we have a different sort of agent in this system called a notary, and we'll see how they are the ones that take the role of verification rather than this public verification that we see on blockchains. Now, importantly, this brings in the trusted third party. A notary is going to be a trusted third party in this environment. So that's a very different than what the goals of Bitcoin. One of the major goals of Bitcoins is like, no, we don't want any trusted third parties to be necessary for this system to work. In the Corda system, we will have trusted third parties, notaries. They have relatively limited roles in what they're verifying, but we do require trust of that third party. So the system depends on those notaries. Transactions reach finality immediately once they're notarized by that notary. So there's not this waiting for sort of subsequent blocks to be verified and add. And then eventually we're like, okay, we're pretty certain this transaction will never be unwound on the blockchain. Okay, no, we're replacing that now with a trusted third-party notary. So instead of asking how can strangers agree without trusting institutions, that's kind of more like a Bitcoin or an Ethereum question. Corda is how can institutions coordinate shared records more efficiently while preserving privacy and legal accountability? So there's really a different motivation here, but a lot of the same logic and tools are applied to answer this second question. So the core economic problem is really shifting in the background when we think about Corda relative to a system like Bitcoin. So Bitcoin focuses on problems like censorship resistance, trust minimization, open participation. Corda focuses on reducing institutional frictions like duplicated record keeping. Because in the traditional system, it's like, I'm going to keep all my records. You're going to keep all your records. We're going to duplicate them across many institutions because I'm not going to trust you to keep track of my money on your record as a potential counterparty to transactions with me. A different way to do that would be to have a system, a software that's verified and say like, hey, we all store all of these transactions in this shared ledger, and then we don't have to duplicate as much if we all trust the shared ledger. So reconciliation costs, as we'll see, so reconciliation costs might be things like, hey, you haven't paid me yet for this transaction we engaged in. Settlement delays, similar. I'm still waiting for payment. Counterparty risk, maybe this person will never pay me. Maybe they'll go bankrupt in the meantime before they get a chance to pay me, and then they'll never pay me. Information leakage between institutions, because we've seen how the tools like encryption and things like hashing messages can help us have information privacy. And so a lot of those same tools will be used in this system. These problems appear in many real financial markets. So trade finance, syndicated loans. A syndicated loan is like a really big loan where there's many different lenders that pool their money to make one loan to one borrower. Securities settlement. So maybe I bought an option, it settles in the money. We need to send money my way because that option should pay off. Derivatives collateral system. So we've also already mentioned derivatives collateral systems, although we didn't maybe talk about it in that way. But hey, here's some Bitcoin as collateral. Give me USD coins so I can bet on silver futures. Silver futures are an example of a derivative. Their value is derived from the underlying value of silver as a commodity. Bitcoin is collateral. That's a derivatives collateral system. Large financial institutions often engage in transactions like that, but they sure as heck aren't going to just go to Ethereum and do that in a permissionless, open way. Because, in part, because of the very highly regulated financial institutions. Tokenized real world assets. So your book has, I'm not going to force you to read most of the rest of the book, actually, but I encourage you to read it. Digital tokens are one of the next sections of the book. A tokenized real world asset is like tokenized silver futures. So it's basically the value of that token that might live on a blockchain is derived. So it's kind of like a derivative from the value of silver. And so there's a bunch of benefits to tokenizing real world assets that can then be traded. They essentially track the value of those real world assets. We could tokenize a stock, and then maybe we tokenize Alphabet stock. Well, the blockchain is open 24/7. So now we could trade those tokenized Google stocks after hours, and that might give us more liquidity in financial markets, more information from financial markets during off hours, based on off hours trading of tokenized assets like stocks or commodity futures. So in this notebook, just to kind of like, we'll, as similar to the past, we'll just write some code that sort of is a toy model of this Corda system. So a Corda style ledger and simulate two real institutional workflows. The two we're going to do is a voucher purchase and redemption. So this is a simple rule-based smart contract example. This might occur. So a gift card to a coffee shop is an example of a voucher. I give you money, you give me a voucher called a gift card, basically, that says, hey, now I have a claim at coffee at your coffee shop. That's not going to be very important to large regulated financial institutions, but we can imagine things like, hey, this person bought a bunch of hog futures. Here's a voucher saying they have a claim on hogs that are delivered to Chicago and during this time period, for example. That could be a voucher on the physical delivery of certain types of assets like hogs or silver or corn. Delivery versus payment. So maybe one financial institution wants to buy an asset from another financial institution. This creates what's called counterparty risk. I'm going to give you money, you're going to give me an asset. If you give me the asset before I give you the money, there's a risk that I don't pay you. I have the asset and my money now. Maybe I go bankrupt during that time period. I'm like, oops, sorry, I went bankrupt before I paid you. The opposite is true too. Maybe I pay you and I haven't received my asset now. Now there's a risk that you don't actually transfer the asset to me. Those are overly simplified examples, but that's what we refer to as counterparty risk. There's a risk that my counterparty in a transaction, the other party in a transaction, will not pay me because they decide not to pay me for some reason. Maybe they actually believe there's a legitimate reason not to pay me. Maybe they'll go bankrupt and they literally cannot pay me. So those types of issues create counterparty risk. So these examples essentially are meant to show how rules and signatures, digital signatures, and a notary, the trusted third party, replace mining in the longest chain rule in selection in permissioned distributed ledgers. So we need to replace those. We have all these rules we set up to verify transactions in a permissionless public ledger. Now we are basically need to say, okay, well, how are we going to replace those when we have a permission ledger? So in Bitcoin, transactions go into the mempool and float around for a while. Maybe there's a large transaction fee on some of those, and then a miner says, hey, I want this transaction on my next block that I'm going to try to mine because I'll get a big fee if I successfully mine that. Some are free, they might float around in the mempool longer, but the mempool is those transactions that haven't yet made it onto a block. Miners then create blocks and add transactions to them, and then consensus emerges through the proof of work and the longest chain rule, essentially, as we've already gone over. In our Corda style system, parties already know who each other are. Me, Bank A, I would like to buy an asset from Bank B, so we know who we are. So I could send sort of a message in the network, like, I would like to make this transaction with you, essentially. Transactions are proposed directly between counterparties. All required parties digitally sign the transaction, and we know all about digital signatures already. That leads to verification. A notary prevents a double spending by basically taking a look and said, okay, these two banks or financial institutions are engaging in this transaction. Do their resources or so the digital currency essentially exists to allow this transaction to go forward? Or did they already spend this in a different transaction? Because if they did, that would lead to a double spending problem. There might be an incentive for some to double spend. So we need to take care of that. How do we take care of that? We have a notary, a trusted third party, take a look at the proposed transaction, decide if it's valid, and then they'll validate it if it is, and say, no, this is not valid if it looks like a double spend or there's other issues. The result of having the notary is we get this finality right away, as opposed to in a blockchain system like Bitcoin, where we're sort of things become more and more verified over time as the blockchain grows. No, here we have immediately finality because our trusted third party validated the transaction. What's the trade-off? We are now dependent on the trusted third party. Is the third party actually trustworthy? Things like that. So we represent ledger facts, so like how much money each bank has, what assets each bank owns as state. So at any given point in time, each financial institution that's participating in this will have some assets in it, will have cash, things like that. At any point in time, the state is all of those different balances. And then if a transaction occurs, that will lead to a new state. And basically what happens is we say, okay, this old state no longer exists. This is the current state of the world. Those old states, which don't still, I shouldn't say don't exist, because a record of them does exist, and a verified record, a hashed record, essentially. So it's not, we can't tamper with the past, but we can audit the past. So all of these are stored, but the current state is the one that represents what's currently, what are the current assets owned by all of our participants, what debts are owed by all of our participants. That will be defined in the current state. That should be traceable up. If we look at all of the past states, we should be able to say, yep, this current state makes sense given the history of all past states. So there is still a flavor of that verified history going on here. It's just the tools we use to verify that history are a little bit different than in a blockchain like Bitcoin. States behave like UTXO objects. So this is an unspent transaction output. That's kind of like Bitcoin, where we have to verify, hey, did somebody already try to spend this old Bitcoin in a different situation? So we have to verify that these are unspent transaction outputs. So that's sort of what the notary does. This UTXO shows up a lot in finance and especially in cryptocurrency finance. So what happens when a transaction occurs is an existing state is consumed because after a transaction, the new state will be different. Money and assets will change hands as a result of transactions on the Corda network. A new state that represents the after the new transactions occur state is created at that moment. The ledger evolves through these state transitions. And as I've already mentioned, this makes it tamper evident because of tools that we already know about, like hashing, and it's auditable. Because if you try to change the history, things will go wrong with the computational tools like hashing, because we know that those are create tamper evidence and things like that. And because of this history of states, we can audit at any time. All right, is the current state consistent with the history of states? So we're going to do a couple of simple examples here to just really walk through, and these are pretty simple examples, but what I really want you to critically think about is how states are being updated, how this leads to tamper evidence, and how it's auditable. And also thinking about the comparing and contrasting to things that are happening on permissionless networks. So suppose Bank A owes Bank B $100. The initial state on the ledger, state one, borrower is Bank A, lender is Bank B. Amount is $100. Standing, there's an outstanding debt or outstanding balance. Now Bank A repays the loan. So that's a transaction. A transaction occurs that consumes the old state, this state right here. So that's going to disappear and become consumed, which means it's no longer the current state. And now state one is consumed. So that was the original state right here. Then a transaction occurs, and now there's a new state. State two, what does state two look like? Well, borrower Bank A, lender Bank B, amount is zero because it was repaid. The status is that it's repaid. So this old state was replaced with this new state that reflects the repayment transaction. The original state is never edited or erased. Instead, it is marked as consumed, and a new state records the updated facts. So this is creating, it's not erased or edited. So we have this tamper evident history. Why is it tamper evident? Because we're using hash functions in the background of the system. So anybody reviewing the ledger, although that's going to be private, so it's not like I can just go review the Corda ledger. But if somebody were to review it, and maybe that could happen, maybe a court case comes and it's like, well, can we prove the history of the transactions? Yes, because we could provide permission for the court to, for example, to review the entire full history and verify, yes, this history is current with it, consistent with this current state of the world, or no, this history is not consistent with this current state of the world. And that's really where now, instead of having people arguing using subjective sort of judgment about what should be the current state of the world, we're going to a tamper evident and audible history stored in a distributed ledger and saying this is now stronger proof about what the history of the world looks like in terms of these transactions and what led to the current state. So now we're going to start. So we just have our close, and it's a little bit more complicated than usual because we have libraries and I've put some helper functions that we'll use for our toy model here. But first, let's just think about, now we're going to start actually building a sort of toy Corda system. And again, these are going to be relatively simple examples, but I want you to think about, okay, what do we need to create this system that we've described? Well, we need participants and a notary. So instead of anonymous miners, we now have institutions like financial institutions are the types of institutions that will participate in this system. We need digital signatures, which is something we needed before. So that's common to permissioned and permissionless systems. And a notary service. So that's going to be something new to this specific Corda system. The notary has one primary job to ensure that an input state is not used twice. Because if we took state one up there, and then bank B could be like, hey, you never repaid me that money, so you need to do it again, that would create double spending essentially. So we only want to consume old states once, and the notary's job is to make sure, okay, we need one unique valid history. Just like we want on Bitcoin. How did we solve it there? Well, oh, we have two histories all of a sudden because this is a permissionless network. We got a fork. Okay, now there's a race for the longest chain, and that will become the shared history. In this case, we replace that with having a trusted notary. They're the ones that are going to verify the history over time. So the notary does not do things that are more subjective, like deciding if something is fair or applying any judgment. All what they're doing is saying, is this consistent with the currently shared history that we've all agreed to? So it only checks that the transaction uses valid inputs. Are there assets available in state one that the transaction moving us to state two is valid? And so making sure that those aren't consumed in some other transaction occurs within its allowed time window. So there might be some time restrictions on when transactions can occur, and the notary will also be verifying that. So this is just some code. So what do we need? We need parties to transactions like bank A and bank B. In my above example would be two parties to the transaction we described up there. I won't go deep into the code, but this is just us building what we need to make the system we just described. Well, if we want to make a toy model of this, we need parties to transactions. Obviously, we need a notary as well, because that plays an important role in this system. Now, ledger states each object on the ledger represents a shared fact. So I owe, or bank A owes bank B $100. That's a shared fact that, like, I am sharing that fact with bank B. And so that's like an example of what a shared fact in the state. So a state is just basically a huge list of shared facts on the system. Transactions then lead to a new list of shared facts in the new state. So cash balances, asset ownership record, vouchers, contract positions, those are all examples of what might be considered share facts in any given state of the world. A state always includes a list of participants because now only participants that matter in terms of the different shared facts are going to be the ones that have access to them. This is what's going to ensure privacy in the sense that we discussed above. So your identity isn't private, but transactions that your identity make will be private in terms of not available to everybody in the system and definitely not available to the public outside of the system, outside of the Corda distributed ledger. So that's one of the biggest differences of Corda with Bitcoin. Bitcoin, everyone sees everything. In Corda, only relevant parties to a transaction see the relevant state before and after that transaction occurs. So what we need, we'll just create, these are different examples of shared facts that we're going to have on our tour. So cash state, there's an owner. So the name of the owner, like bank A. Amount, how much cash do they have? Participants, possibly only that individual needs to be a participant in terms of that. How much cash do they have? We could have a voucher state. So the coffee shop issues vouchers. The customer owns the voucher. The value of the voucher, how much is the voucher worth? Redeemed is a Boolean true. It has been redeemed, so it should no longer be as valuable or have any value, depending on how much was redeemed. And so that's a Boolean, true or false. Participants, probably the issue and the owner in this case, are going to be the main participants to that transaction. Asset state, very similar to a cash state. What is the asset called? Who owns the asset? Participants, maybe there's only one participant in that case as well. So let's do an example actually using this code we've written and do a voucher purchase and redemption. So we begin with a simple Corda style example. Imagine a merchant sells a digital voucher worth $10. Like they sell a coffee card for a Starbucks gift card for $10. Probably wouldn't use Corda for that, but that would be an example of a voucher. The economic problem is straightforward. The customer does not want to pay and then receive nothing, because that would be lame. The merchant does not want to issue the voucher without receiving payment, because that would be lame for them. A rule-based transaction can solve this coordination problem. The idea is the customer starts with a cash state. A transaction consumes that cash state and new states are created. A cash state owned by the merchant. So I have a 10, like say I just have $10 and that's my cash state on Corda. And then I'm going to use that $10 to buy a voucher from the merchant. Well, that transaction kills my cash state. That state no longer exists. It's consumed. And in the new state, I have $0, but we don't really even have to store that as a state. What we will store is that I now own a voucher and the merchant has a new cash state of $10 involved from that transaction. Later, of course, the consumer can redeem the voucher. That redemption is another state transition. The original voucher state is consumed because we also have to show in the system, like Gavin had a voucher for coffee. He bought coffee with it. So the voucher is redeemed. It's no longer valid because it's been used. The new voucher state is created with a redeemed equals true because that was one of our variables in that voucher definition that we looked at a second ago. This lets us see how a ledger can record the history of a claim over time. So we'll create the parties to the transaction. I'm not going to go deeply into that code, but we have a customer. We'll call that. So we're applying basically this party. We're creating a variable that's, we defined party above. Our customer is going to be a party. We're going to name them customer. Merchant is going to be a party named merchant right here. So the notary, of course, we need to verify this transaction. And then we run that. And the initial customer cash state is here is basically the customer's reference, which is a hash output. And the cash state of that referenced customer is an owner. So who is it? That's the customer. The amount is this $10 cash state, and the only participants in that case are going to be the customer, because really only the customer needs to know that they have $10 in the Corda system in this state of the world. In the current state, the customer has $10. Who needs to know that? Just really the customer. So then let's execute a voucher transaction. So voucher purchase. And then I'm going to skip through that code. If you want to talk about the code or what each of those specific things are doing, you will need to change a couple things in here, like maybe amount is one thing you can change. I tried to make this one pretty simple in terms of what you change, really just to get you in here to play with it for this assignment, to just take a closer look at it. And so then we'll print what happens. So customer signed, merchant signed, because we need to sign this transaction using digital signatures. That's how we verify transactions. So then the transaction is notarized. So the notary is checking, okay, do you actually have enough cash to make this transactions? Are these valid signatures is another thing that the notary will be checking. New merchant cash state. So now here's the merchant ID, the cash state of who owns this cash state, the merchant. They have $10 now because in the new state, the $10 from the customer was transferred to the merchant. The participants here are customer and merchant because this relates to that transaction. New voucher state, now the issuer is the merchant, the owner is the customer, value is $10. That's the value of the voucher. It's not redeemed yet, so that is still false. And of course, the participants, the customer and the merchant were involved in this transaction, and they will be able to observe it as participants to the transaction. But there's many participants or parties on the Corda board. Not all those other parties or participants would be able to view this transaction because we define explicitly who can view it for privacy purposes. So then in this block of code, we can execute the voucher, and then we have another transition to really state 3 here, where state 3, customer signed redemption, merchant signed redemption. Redemption is notarized because we need the notary to be involved in every transaction. That's what's verifying these things. Redeemed voucher state. So voucher state, issuer is merchant, owner is customer. The value is still 10, but now the redemption has changed to true as a result of redemption of the voucher. So that basically means Gavin went into the coffee shop. He bought his $10 worth of coffee. So now we need to transition to a new state of the world where the voucher has been redeemed. And that's going to be in this shared history. So if I walk in the next day, I still have my little plastic card and I say, hey, I want $10 worth of coffee. They can say, no, this is already being redeemed. Oh, prove it to me. Okay, we can prove it. It was notarized here. So a trusted third party notarized the fact that it was redeemed. You can see that because you're a participant to that transaction on Corda as the customer and so forth. So it's worth thinking about what is being replaced compared to what we saw on how blockchain ledgers work. Those permissionless blockchain ledgers, how are we doing those on this blockchain now, where we have permission and notaries? So this voucher example highlights several ideas that connect directly to earlier lessons, as in week 4, digital signatures represent authorization. Weeks 5 and 6, a transaction input can only be used once. Unlike Bitcoin, agreement here does not come from mining or the longest chain. Instead, agreement comes from signatures by the relevant parties and a notary preventing reuse of the same state. Because maybe in the background, to think about what's going on with that, the notary maybe has a wider view and they can see, well, did Gavin try to use his cash state to pay a different merchant? Maybe he's trying to do both of those things at the same time to do a double spend. And then I'm getting $20 out of purchasing power out of my $10. The notary's role now is to check that. And versus Bitcoin, the public basically checks that for us. So this is already enough to create a useful institutional ledger. We now move to a more recognizably financial example. So example 2, let's do two-party delivery versus payment trade. Delivery versus payment means that delivery and payment occur simultaneously to reduce counterparty risk. We described above how if there's any delay in either direction, delay in payment or delay in delivery of an asset, that creates counterparty risk. Delivery versus payment means these are going to happen at one time, and that's called an atomic sort of nature of the transaction. The transaction is the atomistic unit. It's not like the payment is part of it, the delivery is part of it. When we put those two atoms together, we get a transaction. No, in Corda, the entire transaction is the atomistic unit. That creates this delivery versus payment happening at the same time and reduces dramatically counterparty risk to make sure those things happen simultaneously through definitions in smart contracts, verified and final the second the notary takes a look at it, confirms that somebody's not trying to double spend, basically. So a classic institutional transaction, Bank A has some cash, Bank B holds an asset, and they want to trade. Bank A wants to buy the asset with its cash. The important economic issue is settlement risk. If the cash moves first, Bank A is exposed. If the asset moves first, Bank B is exposed. Delivery versus payment solves this problem by making the two legs occur together at the same time. It literally essentially defines them as one thing. In state transition language, the old cash state is consumed, the old asset state is consumed, new states are created. Cash owned by Bank B, asset owned by Bank A. So in the new state, we have the reversal of the initial state. This is one reason permission ledgers are attractive in financial markets. They can make settlement atomic. So that means that that's the atomistic unit is the transaction itself and not just like the independent pieces of the transaction, like moving cash separately than moving assets. No, we're going to define that as the atomistic unit. They're final because of the notarization, and they're auditable because of the saved consume history of states that lead logically to the current state. So we have initial cash assets. So we have Bank A, they have 100. Oh, they only need to know that they're the only participant to that cash state. Asset state, only Bank B really knows. Although of course, it becomes Bank A is essentially come aware that Bank B has an asset that they want to buy. That could happen through face-to-face negotiations. And then we could say, okay, let's go use Corda to actually implement this transaction. So we're going to do a delivery versus payment trade transaction. That will, of course, update to the states to the opposite. Cash state, owner bank B, amount 100. Now we have two participants because they both are party to this transaction that move cash to bank B. Both are also parties to the transaction, the same transaction that shifted us to this new state. Both are participants. And we see that now they have the bond 001, as we named it, asset. So the economic interpretation of all this, these two examples show what changes when we move from a Bitcoin style blockchain to a Corda style institutional ledger. In Bitcoin style systems, transactions are broadcast publicly, ordering is achieved through proof of work, agreement through the longest chain rule. Temporary disagreement is allowed. Finality is probabilistic. So ultimate verification of transactions is probabilistic. Probability that it will always be verified gets higher and higher as the blockchain grows. In this toy Corda style system, transactions are proposed directly between relevant parties. Parties sign to indicate authorization and agreement, which that is similar to other blockchains and other digital payment and cash systems that we've seen. A notary prevents double spending of states, so that brings back in our trusted third party. Very big difference from Bitcoin and Ethereum blockchains. Once notarized, the transaction is final. So that's deterministically final, but it does depend on the trust of that notary. So this is really just me repeating things from the introduction, so I won't waste much of your time there. But now just bigger picture, what this means for the economics of financial infrastructure. These toy examples help illustrate why systems like Corda matter. They are not designed mainly to solve the Bitcoin problem of anonymous global consensus. They're designed to solve a different problem. They are designed to solve institutional problems like reconciliation costs, settlement risk, duplicated record keeping. So because that's costly, storing it for power, also having it be unduplicated, but in a shared ledger helps us with verification and trust in many ways. If everybody sees, okay, we have an auditable, tamper-resistant history of transactions, there's going to be a more trust among participants in that system, which will allow people to take maybe economically beneficial risks in other ways by reducing these types of risks and costs. Privacy between counterparties is something that we want in regulated financial systems for reasons that I mentioned earlier. Like maybe there's transactions that feed directly into their business strategy that they want to be private. Legally attributable state changes. So legally attributable state changes, because maybe this is a very strong, as I mentioned before, history that could be used in something like court, that could be shown to a judge or shown to lawyers as a very strong proof of the history that led to the current state of the world, which defines who owns assets, how much cash should everybody have based on the history of the system. Of course, Corda was built using a lot of the same tools as a Bitcoin, but those tools can be arranged in different ways to achieve solutions to different types of problems that may be more present in heavily regulated financial institutions, as we are very common in the United States and globally. All right, so don't hesitate to reach out if you have any questions about this stuff. This is one of the growing areas sort of on the frontier of a lot of the technologies we've been learning about for the more traditional banking system. And those are becoming increasingly intertwined, as we saw in the article at the beginning of the lecture. And so things are changing quickly. I think it's exciting. There's a lot of different stuff going on. Hopefully this was an interesting example of one of the many changes that are occurring as a result of this new technology. Okay. Again, don't hesitate to reach out if you have questions, and I will see you next time.